Well logging, also known as borehole logging, is the practice of making a detailed record of the geologic formations penetrated by a borehole. The log may be based either on visual inspection of samples brought to the surface or on physical measurements made by instruments lowered into the hole. Some types of geophysical well logs can be done during any phase of a well's history: drilling, completing, producing, or abandoning. Well logging is performed in boreholes drilled for the oil and gas, groundwater, mineral and geothermal exploration, as well as part of environmental and geotechnical studies. Wireline logging. The oil and gas industry uses wireline logging to obtain a continuous record of a formation's rock properties. Wireline logging can be defined as being the acquisition and analysis of geophysical data performed as a function of well bore depth, together with the provision of related services. Note that wireline logging and mud logging are not the same, yet are closely linked through the integration of the data sets. The measurements are made reference to true along hole depth. These and the associated analysis can then be used to infer further properties, such as hydrocarbon saturation and formation pressure, and to make further drilling and production decisions. Wireline logging is performed by lowering a logging tool or a string of one or more instruments on the end of a wireline into an oil well and recording petrophysical properties using a variety of sensors. Logging tools developed over the years measure the natural gamma ray, electrical, acoustic, stimulated radioactive responses, electromagnetic, nuclear magnetic resonance, pressure and other properties of the rocks and their contained fluids. For this article, they are broadly broken down by the main property that they respond to. The data itself is recorded either at surface, or in the hole to an electronic data format, and then either a printed record or electronic presentation called a well log is provided to the client, along with an electronic copy of the raw data. Well logging operations can either be performed during the drilling process, to provide real-time information about the formations being penetrated by the borehole, or once the well has reached total depth and the hole depth of the borehole can be logged. Real-time data is recorded directly against measured cable depth. Memory data is recorded against time, and then depth data is simultaneously measured against time. The two data sets are then merged using the common time base to create an instrument response versus depth log. Memory recorded depth can also be corrected in exactly the same way as real-time corrections are made, so there should be no difference in the attainable accuracy. The measured cable depth can be derived from a number of different measurements, but is usually either recorded based on a calibrated wheel counter, or using magnetic marks which provide calibrated increments of cable length. The measurements made must then be corrected for elastic stretch and temperature. There are many types of wireline logs and they can be categorized either by their function or by the technology that they use. Open hole logs are run before the oil or gas well is lined with pipe or cased. Cased hole logs are run after the well is lined with casing or production pipe. Wireline logs can be divided into broad categories based on the physical properties measured. History Conrad and Marcel Schlumberger, who founded Schlumberger Limited in 1926, are considered the inventors of electric well logging. Conrad developed the Schlumberger array, which was a technique for prospecting for metal ore deposits, and the brothers adapted that surface technique to subsurface applications. On September 5, 1927, a crew working for Schlumberger lowered an electric sondor tool down a well in Peckelbronn, Alsace, France, creating the first well log. In modern terms, the first log was a resistivity log that could be described as 3.5-meter upside-down lateral log. In 1931, Henri Georges Doll and G. Deschâtel, working for Schlumberger, discovered that the galvanometer wiggled even when no current was being passed through the logging cables down in the well. This led to the discovery of the spontaneous potential, which was as important as the ability to measure resistivity. The SP effect was produced naturally by the borehole mud at the boundaries of permeable beds. By simultaneously recording SP and resistivity, loggers could distinguish between permeable oil-bearing beds and impermeable non-producing beds. In 1940, Schlumberger invented the spontaneous potential dipmeter. This instrument allowed the calculation of the dip and direction of the dip of a layer. The basic dipmeter was later enhanced by the resistivity dipmeter and the continuous resistivity dipmeter. Oil-based mud was first used in Rangeley Field, Colorado in 1948. Normal electric logs require a conductive or water-based mud, but OBMs are non-conductive. The solution to this problem was the induction log, developed in the late 1940s. The introduction of the transistor and integrated circuits in the 1960s made electric logs vastly more reliable. Computerization allowed much faster log processing, and dramatically expanded log data gathering capacity. The 1970s brought more logs and computers. These included combo-type logs where resistivity logs and porosity logs were recorded in one pass in the borehole. The two types of porosity logs date originally from the 1940s. Sonic logs grew out of technology developed during World War II. Nuclear logging has supplemented acoustic logging, but acoustic or sonic logs are still run on some combination logging tools. Nuclear logging was initially developed to measure the natural gamma radiation emitted by underground formations. However, the industry quickly moved to logs that actively bombard rocks with nuclear particles. The gamma-ray log, measuring the natural radioactivity, was introduced by Well Surveys Incorporated in 1939, and the WSI Neutron log came in 1941. The gamma-ray log is particularly useful as shale beds which often provide a relatively low permeability cap over hydrocarbon reservoirs usually display a higher level of gamma radiation. These logs were important because they can be used in cased wells. WSI quickly became part of lane wells. During World War II, the U.S. government gave a near-wartime monopoly on open-hole logging to Schlumberger, and a monopoly on cased-hole logging to lane wells. Nuclear logs continued to evolve after the war. The nuclear magnetic resonance log was developed in 1958 by Borg-Warner. Initially the NMR log was a scientific success but an engineering failure. However, the development of a continuous NMR logging tool by Numa is a promising new technology. Many modern oil and gas wells are drilled directionally. At first, loggers had to run their tools somehow attached to the drill pipe if the well was not vertical. Modern techniques now permit continuous information at the surface. This is known as logging while drilling or measurement while drilling. MWD logs use mud pulse technology to transmit data from the tools on the bottom of the drill string to the processors at the surface. Electrical logs equals resistivity log. Resistivity logging measures the subsurface electrical resistivity, which is the ability to impede the flow of electric current. This helps to differentiate between formations filled with salty waters and those filled with hydrocarbons. Resistivity and porosity measurements are used to calculate water saturation. Resistivity is expressed in ohms or ohms/meter, and is frequently charted on a logarithm scale versus depth because of the large range of resistivity. The distance from the borehole penetrated by the current varies with the tool, from a few centimeters to 1 meter. Image log. Image logs use a rotating transducer to measure acoustic impedance across the entire borehole wall. This can then be used to identify the presence and direction of rock fractures, as well as understanding the dip direction of the stratigraphy. Porosity logs equals, porosity logs measure the fraction or percentage of pore volume in a volume of rock. Most porosity logs use either acoustic or nuclear technology. Acoustic logs measure characteristics of sound waves propagated through the wellbore environment. Nuclear logs utilize nuclear reactions that take place in the downhole logging instrument or in the formation. Nuclear logs include density logs and neutron logs, as well as gamma-ray logs which are used for correlation. The basic principle behind the use of nuclear technology is that a neutron source placed near the formation whose porosity is being measured will result in neutrons being scattered by the hydrogen atoms, largely those present in the formation fluid. Since there is little difference in the neutrons scattered by hydrocarbons or water, the porosity measured gives a figure close to the true physical porosity, whereas the figure obtained from electrical resistivity measurements is that due to the conductive formation fluid. The difference between neutron porosity and electrical porosity measurements therefore indicates the presence of hydrocarbons in the formation fluid. Density. The density log measures the bulk density of a formation by bombarding it with a radioactive source and measuring the resulting gamma ray count after the effects of Compton's scattering and photoelectric absorption. This bulk density can then be used to determine porosity. Neutron porosity. The neutron porosity log works by bombarding a formation with high-energy epithermal neutrons that lose energy through elastic scattering to near thermal levels before being absorbed by the nuclei of the formation atoms. Depending on the particular type of neutron logging tool, either the gamma ray of capture, scattered thermal neutrons or scattered, higher-energy epithermal neutrons are detected. The neutron porosity log is predominantly sensitive to the quantity of hydrogen atoms in a particular formation, which generally corresponds to rock porosity. Boron is known to cause anomalously low neutron tool count rates due to it having a high capture cross-section for thermal neutron absorption. An increase in hydrogen concentration in clay minerals has a similar effect on the count rate. Sonic. A sonic log provides a formation interval transit time, which typically varies lithology and rock texture but particularly porosity. The logging tool consists of a piezoelectric transmitter and receiver, and the time taken for the sound wave to travel the fixed distance between the two is recorded as an interval transit time. Lithology logs equals gamma ray. A log of the natural radioactivity of the formation along the borehole, measured in API. Particularly useful for distinguishing between sands and shales in a siliclastic environment. This is because sandstones are usually non-radioactive quartz, whereas shales are naturally radioactive due to potassium isotopes in clays, and adsorbed uranium and thorium. Self-spontaneous potential. The spontaneous potential log measures the natural or spontaneous potential difference between the borehole and the surface, without any applied current. It was one of the first wireline logs to be developed, found when a single potential electrode was lowered into a well and a potential was measured relative to a fixed reference electrode at the surface. The most useful component of this potential difference is the electrochemical potential because it can cause a significant deflection in the SP response opposite permeable beds. The magnitude of this deflection depends mainly on the salinity contrast between the drilling mud in the formation water and the clay content of a permeable bed. Therefore, the SP log is commonly used to detect permeable beds and to estimate clay content and formation water salinity. Miscellaneous Caliper. A tool that measures the diameter of the borehole, using either 2 or 4 arms. It can be used to detect regions where the borehole walls are compromised and the well logs may be less reliable. Nuclear magnetic resonance. Nuclear magnetic resonance logging uses the NMR response of a formation to directly determine its porosity and permeability, providing a continuous record along the length of the borehole. Spectral noise logging. Spectral noise logging is an acoustic noise measuring technique used in oil and gas wells for well integrity analysis, identification of production and injection intervals and hydrodynamic characterization of the reservoir. SNL records acoustic noise generated by fluid or gas flow through the reservoir or leaks in downhole well components. Noise logging tools have been used in the petroleum industry for several decades. As far back as 1955, an acoustic detector was proposed for use in well integrity analysis to identify casing holes. Over many years, downhole noise logging tools proved effective in inflow and injectivity profiling of operating wells, leak detection, location of crossflows behind casing, and even in determining reservoir fluid compositions. Robinson described how noise logging can be used to determine effective reservoir thickness. Logging while drilling. In the 1970s, a new approach to wireline logging was introduced in the form of logging while drilling. This technique provides similar well information to conventional wireline logging, but instead of sensors being lowered into the well at the end of wireline cable, the sensors are integrated into the drill string and the measurements are made in real time, whilst the well is being drilled. This allows drilling engineers and geologists to quickly obtain information such as porosity, resistivity, hole direction and weight on bit, and they can use this information to make immediate decisions about the future of the well and the direction of drilling. In LWD, measured data is transmitted to the surface in real time via pressure pulses in the well's mud fluid column. This mud telemetry method provides a bandwidth of less than 10 bits per second, although, as drilling through rock is a fairly slow process, data compression techniques mean that this is an ample bandwidth for real-time delivery of information. A higher sample rate of data is recorded into memory and retrieved when the drill string is withdrawn at bit changes. High-definition downhole and subsurface information is available through networked or wired drill pipe that deliver memory-quality data in real time. Memory log equals. This method of data acquisition involves recording the sensor data into a downhole memory, rather than transmitting real-time to surface. There are some advantages and disadvantages to this memory option. The tools can be conveyed into wells where the trajectory is deviated or extended beyond the reach of conventional electric wireline cables. This can involve a combination of weight-to-strength ratio of the electric cable over this extended reach. In such cases the memory tools can be conveyed on pipe or coil tubing. The type of sensors are limited in comparison to those used on electric line, and tend to be focused on the cased hole, production stage of the well. Although there are now developed some memory open-hole compact formation evaluation tool combinations. These tools can be deployed and carried downhole concealed internally in drill pipe to protect them from damage while running in the hole, and then pumped out the end at depth to initiate logging. Other basic open-hole formation evaluation memory tools are available for use in commodity markets on slickline to reduce costs and operating time. In cased hole operation there is normally a slickline intervention unit. This uses a solid mechanical wire, to manipulate or otherwise carry out operations in the wellbore completion system. Memory operations are often carried out on this slickline conveyance in preference to mobilizing a full-service electric wireline unit. Since the results are not known until return to surface, any real-time well dynamic changes cannot be monitored real-time. This limits the ability to modify or change the well downhole production conditions accurately during the memory logging by changing the surface production rates. Something that is often done in electric line operations. Failure during recording is not known until the memory tools are retrieved. This loss of data can be a major issue on large offshore locations. On land locations where there is what is called a commodity oil service sector, where logging often is without the rig infrastructure. This is less problematic, and logs are often run again without issue. Coring. Coring is the process of obtaining an actual sample of a rock formation from the borehole. There are two main types of coring: full coring, in which a sample of rock is obtained using a specialized drill bit as the borehole is first penetrating the formation, and sidewall coring, in which multiple samples are obtained from the side of the borehole after it has penetrated through a formation. The main advantage of sidewall coring over full coring are that it is cheaper and multiple samples can be easily acquired, with the main disadvantages being that there can be uncertainty in the depth at which the sample was acquired and the tool can fail to acquire the sample. Mud logging. Mud logs are well logs prepared by describing rock or soil cuttings brought to the surface by mud circulating in the borehole. In the oil industry they are usually prepared by a mud logging company contracted by the operating company. One parameter a typical mud log displays is the formation gas. The gas recorder usually is scaled in terms of arbitrary gas units, which are defined differently by the various gas detector manufacturers. In practice, significance is placed only on relative changes in the gas concentrations detected. The current oil industry standard mud log normally includes real-time drilling parameters such as rate of penetration, lithology, gas hydrocarbons, flow line temperature and chlorides, but may also include mud weight, estimated pore pressure and corrected D-exponent for a pressure pack log. Other information that is normally notated on a mud log include directional data, weight on bit, rotary speed, pump pressure, pump rate, viscosity, drill bit info, casing shoe depths, formation tops, mud pump info, to name just a few. Information use. In the oil industry, the well and mud logs are usually transferred in real time to the operating company, which uses these logs to make operational decisions about the well, to correlate formation depths with surrounding wells, and to make interpretations about the quantity and quality of hydrocarbons present. Specialists involved in well log interpretation are called log analysts. See also, drilling mud, drilling rig, formation evaluation, well control, geosteering, list of oil field service companies, log ASCII standard, digital log information standard, wireline. References. External links: Society of Petrophysicists and Well Log Analysts,